Hello there, and welcome to Sleepy Science Vault. Somewhere out there, beyond the reach of our eyes, entire worlds are drifting through the dark, waiting to be noticed. Tonight, let's slip quietly into that vastness, and think about the planets we have not yet seen. For centuries, humans looked up at the night sky and wondered if we were alone. Wondered if, among those scattered points of light, there might be another Earth. A planet with oceans, with mountains, with skies that shift from blue to orange as a sun rises somewhere far from here. Scientists call these Earth-like worlds especially interesting, because some of them may sit inside what is known as the habitable zone. That gentle band of space around a star, not too close, not too far, where temperatures could allow liquid water to exist on the surface. Not too hot to boil away. Not too cold to freeze solid. Just balanced. The way Earth is balanced. But here is something worth sitting with for a moment. The search for life is not simply about finding planets that look promising. It is about something deeper. Something more exact. The real goal is to find unmistakable signs of current life. Not old fossils. Not ancient echoes. But evidence that something, somewhere, is alive right now. That distinction matters. A planet can look perfect on paper and still be silent. Still be empty. So scientists are patient. They are careful. They know that hope is not evidence, and wonder is not proof. And yet, that hope is part of what keeps the search alive. Now, let's talk about the worlds themselves. The ones we've already found. An exoplanet is simply a planet outside our solar system, orbiting a star that is not our sun. That is the basic definition. Simple, on the surface. But the reality, once you look closer, is far stranger and far more beautiful than that single sentence suggests. Because not every exoplanet even has a star to call home. NASA has confirmed that some exoplanets are what scientists call rogue planets. Worlds that drift through the galaxy without orbiting anything at all. No sun to warm them. No steady orbit to hold them in place. Just endless motion through cold, silent space. Imagine that for a moment, a planet with no day, no dawn, no star to greet it. Only darkness, stretching in every direction, forever. It is a strange kind of freedom. And a strange kind of loneliness. Most exoplanets, of course, do orbit something. And the variety among them is almost hard to believe. There are rocky super-Earths, planets larger than our own, but still solid, still stone beneath their surface. There are many Neptunes, sometimes described as fluffy, worlds wrapped in thick atmospheres, soft and swollen compared to the hard ground we know. And then there are the giants. Planets so large they make our own world look like a pebble beside a boulder. NASA's confirmed exoplanet list reads almost like a catalog of impossible things. Rocky worlds. Gas giants. Hot Jupiters, scorched by their closeness to their stars. And planets that orbit not one sun, but two. Twin suns, rising and setting together, casting double shadows across alien ground. Try to picture that sky. Two sunsets blending into one another. two warm lights sinking below a horizon that belongs to no one we've ever met. And it goes further still. Some exoplanets orbit the collapsed remnants of dead stars. Stars that once burned bright, and then ended. Collapsed inward. Became something dense and quiet and strange. And even there, in that graveyard of old starlight, planets continue to circle. Faithful. Undisturbed. Orbiting the memory of a sun that no longer shines the way it used to. There is something quietly moving about that. A planet, still turning, long after its star has changed forever. More recently, NASA's exoplanet records have added something with an unusual name. Superpuff planets. Giant worlds, but strangely light. Very low density, as if some of these planets were built more from air than from stone. Enormous in size, yet almost weightless in comparison to their volume. Space, it seems, still has a sense of surprise left in it. And now, let's step back. Let's think bigger. Scientists estimate that there may be, on average, at least one planet around every star in our galaxy. Let that settle for a moment. Not one planet around a few special stars, but one planet, on average, around every star. In our galaxy, the Milky Way, is filled with stars beyond ordinary comprehension. That estimate implies something almost too large to hold in the mind. Roughly 1 trillion planets, scattered throughout the Milky Way alone. 1 trillion. Some rocky. Some gaseous. Some drifting alone in the dark, with no star at all. Some circling twin suns. Some orbiting the quiet remains of stars that died long before humans ever existed. And this is only our galaxy. One galaxy, among countless others. So take a slow breath, and let that number settle over you like a blanket. 1 trillion worlds. 1 trillion untold stories. Most of them silent. Most of them unseen. But out there, somewhere, among all of that vastness, perhaps, just perhaps, one of them is not so different from home. For now, let it be enough to imagine them. Quiet. Distant. Endless. And let that vastness carry you gently, toward sleep. The story of how we came to believe in other Earths does not begin with a grand discovery of a twin planet. It begins, quite humbly, with a wobble. In 1995, astronomers turned their instruments toward a star much like our own Sun, a star called 51 Pegasi. And what they found there changed the course of an entire field of science. For the first time, researchers confirmed a planet orbiting a normal, Sun-like star beyond our solar system. It was called 51 Pegasi b. And its discovery marked the true beginning of the modern search for worlds like ours. But here is the twist. 51 Pegasi b was nothing like Earth at all. It was a hot gas giant, massive and scorched, locked into an orbit so tight that a single year on that planet lasted just over 4 days. 4 days. Imagine that. A planet racing around its star so quickly that seasons, if they existed at all, would blur past in a matter of hours. There were no oceans there. No stable ground. No gentle blue skies. just a swirling giant, blistering under the heat of a sun it circled far too closely. And yet, despite being nothing like our world, this discovery mattered enormously. Because it proved something profound. It proved that planets could exist around stars similar to our Sun, not just in theory, but in observable, measurable reality. It opened a door that had been closed for all of human history. And once that door opened, scientists could not stop looking through it. What is perhaps most remarkable is how this planet was found. Astronomers did not see it directly. They did not capture a photograph of a distant world drifting across the black canvas of space. Instead, they watched the star itself. They watched it wobble. You see, a planet does not simply orbit its star in perfect stillness, with the star remaining motionless at the center. Gravity works both ways. As a planet moves through its orbit, its gravity tugs gently on the star it circles. And the star, in response, shifts ever so slightly. It sways. It wobbles, almost imperceptibly, back and forth. That tiny motion, hidden within the light of a star trillions of miles away, was the clue that revealed 51 Pegasi b. Scientists measured that faint stellar sway, and in doing so, confirmed that something unseen was tugging on the star from the darkness beyond it. This detail matters more than it might first seem, because it reveals something essential about how we search for other worlds. In almost all cases, we do not see exoplanets directly. Their light is far too faint, drowned out entirely by the blinding brilliance of the stars they orbit. Trying to spot a small planet beside its star is a little like trying to notice a firefly hovering beside a lighthouse, from thousands of miles away. So instead, scientists rely on indirect methods. Clues. Patterns. Subtle changes that hint at a hidden presence, even when that presence cannot be seen with our own eyes. The wobble method, the one that revealed 51 Pegasi b, is known today as the radial velocity method. It works by carefully measuring that tiny back and forth motion of a star, caused by the gravitational pull of an orbiting planet. As the planet swings toward us in its orbit, the star gets pulled slightly in our direction. As the planet swings away, the star gets pulled slightly away from us too. This creates a rhythmic pattern, a heartbeat of sorts, hidden in the starlight. By studying that pattern closely, scientists can learn remarkable things. The strength of the wobble can reveal how massive the hidden planet is. And the timing of that wobble, how quickly it repeats, can reveal how far the planet sits from its star. A slow, gentle wobble might suggest a planet orbiting from a great distance. A fast, dramatic wobble might suggest a planet whipping closely around its star, the way 51 Pegasi b once did. It is a quiet kind of detective work. No direct glimpse of the planet itself, only the evidence it leaves behind, written softly into the motion of its star. But the radial velocity method is not the only tool astronomers use. There is another approach, one that relies not on movement, but on light itself, and on the smallest of changes within that light. Imagine watching a distant star, night after night, its brightness steady and familiar. And then, every so often, just for a little while, that brightness dims. Just slightly. just enough to notice if you are watching closely enough. And then, after a short while, the light returns to normal. That gentle dimming happens when a planet passes directly in front of its star, from our point of view here on Earth. As the planet crosses that path, it blocks a tiny fraction of the star's light, just enough to cause a small, measurable dip in brightness. This is known as the transit method. It sounds almost too delicate to be useful, but the tools we have built are precise enough to catch it. Astronomers monitor stars continuously, watching for these faint dips with extraordinary patience. When a dip appears, and then appears again, at a regular, repeating interval, it suggests something is passing in front of that star again and again, on a steady orbit. A planet, quietly crossing the same path, time after time. And just like the wobble method reveals a planet's mass and distance, the transit method offers its own kind of insight. The size of that brightness dip, how much light is blocked during each crossing, can help scientists estimate how large the planet actually is. A larger planet blocks more light as it passes. A smaller planet blocks only the faintest whisper of brightness, barely noticeable at all. Together, these two methods, the wobble of radial velocity and the dimming of a transit, offer a way to reconstruct an entire portrait of a distant world, without ever laying eyes on it directly. One method whispers about mass and distance. The other whispers about size. And when combined, they can even reveal a planet's density, hinting at whether that world is likely rocky and solid, or vast and gaseous. It is worth pausing here, just for a moment, to appreciate how astonishing this process really is. Humans, standing on a small rocky planet, orbiting an unremarkable star, tucked into the outer edge of one galaxy among countless others, have learned to detect the presence of worlds we will likely never visit. Worlds we cannot see. Worlds whose only evidence is a flicker of dim starlight, or a barely perceptible tremor in the motion of a distant sun. And of these two remarkable techniques, one has proven especially powerful. The transit method, that gentle dimming of starlight, has become the most successful tool in this search. In fact, about 3/4 of all known exoplanets have been discovered using this very method. 3 out of every 4 worlds we know about, found not by sight, not by sound, but by watching patiently for the faintest shadow crossing the face of a star. There is something deeply peaceful about that idea, if you sit with it for a while. That so much of what we understand about the universe comes not from dramatic, sudden revelations, but from quiet, careful observation. From watching the same point of light, night after night, waiting for the smallest of changes. From trusting that patience, over time, reveals truths that cannot be rushed. Long before we ever find a planet that truly mirrors our own, it is this patience that leads the way. Astronomers, watching the sky in silence. Instruments, tuned to detect the faintest wobble, the gentlest dimming. Small signals, carried across unimaginable distances, eventually reaching us, here, on this quiet blue world. And each one of those signals represents a planet. A place. Perhaps rocky, perhaps gaseous, perhaps blisteringly hot, like 51 Pegasi b, or perhaps, just perhaps, something closer to what we call home. We do not know yet. Not entirely. But the search continues, one faint signal at a time. So for now, let your mind rest on that image. A distant star, glowing quietly in the dark. Ever so slightly, it wobbles. Ever so briefly, it dims. And somewhere, hidden within that flicker, a planet moves silently through its orbit, unseen, but not unknown. Finding a true twin of Earth is not simply a matter of pointing a telescope at the sky and waiting for an answer to appear. It requires scale. It requires patience on a level that is almost difficult to imagine. And it requires instruments so sensitive that they can notice changes far smaller than anything the human eye could ever perceive. This is where missions like Kepler enter the story. Kepler was not designed to study a single star, or even a handful of stars. It was built to watch an enormous number of stars all at once, continuously, night after night, for years at a time. Because if you want to catch the faint dimming caused by a planet crossing in front of its star, you cannot simply guess where to look. You have to watch everything you can, all the time, and let the data reveal which stars are hiding planets and which are not. Think about the sheer scale of that task. Thousands upon thousands of stars, monitored simultaneously, their brightness recorded again and again, searching for the smallest of flickers. It is less like searching for a needle in a haystack, and more like watching an entire field of haystacks, waiting for a single piece of straw to shift ever so slightly out of place. And here is where the real difficulty begins. When a planet the size of Earth passes in front of its star, the dip in brightness it creates is astonishingly small. Less than 1/10%. To put that into perspective, imagine standing far away from a lit window, and watching as a tiny insect drifts briefly across that light. The change would be almost impossible to notice with the naked eye. And yet, this is the scale of change that scientists must detect, not with their eyes, but with instruments precise enough to measure light with extraordinary accuracy. An Earth-sized planet, in other words, barely announces its presence at all. It leaves only the faintest whisper of evidence behind, a flicker so small that only the most sensitive tools can hope to catch it. The challenge becomes even more delicate when we turn to the other major detection method, the wobble of a star, caused by a planet's gravity. For a planet similar to Earth, orbiting a star similar to our Sun, that wobble may only measure around 9 centimeters per second. Let that sink in for a moment. 9 centimeters per second. That is barely faster than a slow, gentle walk. And scientists are attempting to detect that motion, not in something nearby, not in something we can touch, but in a star, trillions of miles away, glowing softly in the darkness of space. It is a wobble so small that it pushes even our most advanced instruments to the very edge of what they are capable of measuring. Every improvement in technology, every refinement in precision, brings us closer to reliably detecting motion this subtle. But we are, quite literally, working at the limits of what current science can achieve. This is why confirming a planet is rarely instant. It is rarely simple. In most cases, scientists must observe several transits, several of those faint dimming events, before they can feel confident that a planet is truly there, and not simply the result of noise, or a passing anomaly, or some other natural fluctuation in starlight. One dimming event might be a coincidence. But if that same faint dip repeats itself again and again at a steady, predictable interval, then confidence begins to grow. A pattern like that is far more difficult to explain away. This process takes time. Sometimes months. Sometimes years. Because if a planet takes a long time to complete a single orbit around its star, scientists may need to wait an equally long time just to witness a second transit, and even longer to witness a third. Patience, in this field, is not simply a virtue. It is a requirement. That said, the field is not standing still. In recent years, researchers have developed newer approaches that can sometimes confirm a planet after observing just a single transit, rather than waiting for the traditional multiple confirmations. By carefully analyzing the shape, timing, and characteristics of that one event, and comparing it against other available data, scientists can sometimes reach a confident conclusion much sooner than before. It does not replace the traditional approach entirely, but it offers a faster path forward in certain cases, saving valuable time in a search that often stretches across years. Now, let's turn to a different kind of challenge altogether. One that returns us to that earlier idea, the near impossibility of actually seeing a planet directly. Indirect detection, through wobbles and brightness dips, has allowed us to infer the existence of thousands of worlds. But actually capturing a direct image of a planet, an actual picture, however small or blurred, is an entirely different level of difficulty. The reason comes down to light, and the overwhelming imbalance between a planet and its star. A star is a source of tremendous brightness, blazing with the light of ongoing nuclear fusion. A planet, by comparison, produces little or no light of its own. It only reflects a small fraction of the light it receives from its star. So when astronomers attempt to photograph a distant solar system, the star's glare is so intense that it drowns out the planet almost completely, like trying to notice a single candle flickering beside the blinding light of a lighthouse beam. This challenge grows even more extreme when the planet in question is small and rocky, the very kind of world we hope to find, if we are searching for something like Earth. Giant planets, massive and often glowing faintly with their own residual heat, are somewhat easier to photograph directly, though still remarkably difficult. But a small, rocky, Earth-like planet reflects only a tiny amount of light, and sits impossibly close to its star from our vantage point across such vast distances. The star's glare simply overwhelms it. At this point in our technological development, directly imaging a true Earth twin remains largely out of reach, a goal still waiting on the horizon of future innovation. There are other methods too, each with its own strengths and its own limitations. One such method is called microlensing. It relies on a strange and beautiful effect predicted by Einstein's theory of general relativity, the idea that gravity itself can bend light. When a massive object, like a star, passes in front of a more distant star from our point of view, its gravity acts almost like a lens, briefly magnifying and bending the light from that background star. If a planet happens to be orbiting that closer star, it can create a small, additional shift in that magnification, a brief secondary clue, hidden within the larger gravitational lensing event. Microlensing has allowed astronomers to detect planets that other methods might miss entirely, including some at extraordinary distances from Earth. But it is far less effective when it comes to smaller, rocky planets. The signal it produces for such small worlds is often too faint, too easily lost within the broader lensing effect, making it a less reliable tool for finding planets that closely resemble our own. And then, there is one more technique worth mentioning, a subtle method known as relativistic beaming. This approach relies on tiny shifts in a star's brightness, caused by its motion toward or away from us, tied closely to the physics of relativity. As a star moves slightly in our direction due to the gravitational pull of an orbiting planet, its light can appear ever so slightly brighter. As it moves away, that light can appear ever so slightly dimmer. It is an elegant idea, rooted deeply in the strange behavior of light and motion at a cosmic scale. But like microlensing, relativistic beaming is not particularly useful for detecting Earth-like worlds. The effect it produces is far too small when the planet in question is a small, rocky world rather than a massive gas giant. It remains a valuable tool in certain specific studies, but not the kind of tool likely to lead us to the next Earth. So here we are, at the edge of what current technology allows. Every method we have discussed, the gentle dimming of a transit, the subtle wobble of radial velocity, the rare bending of light through microlensing, the delicate shifts of relativistic beaming, each carries its own strengths and its own significant limitations. None of them offer a perfect window into these distant worlds. Instead, they offer fragments, clues, small pieces of a much larger puzzle, painstakingly assembled over years of careful observation. And when it comes to worlds most similar to our own, small, rocky, gently orbiting a calm and steady star, these methods are pushed to their absolute limits. The signals are faint. The evidence is subtle. And confirmation often requires years of patient, repeated observation before scientists can say, with real confidence, that a new world has been found. It is humbling, in a quiet sort of way, to consider how much effort goes into finding something so small, so distant, and so easily hidden by the blinding light of its own star. And yet, that effort continues. Instruments grow more precise. Techniques grow more refined. And with each passing year, we inch closer to the kind of clarity that once felt impossible. Somewhere out there, hidden in the glare of a distant sun, there may be a small and rocky world, quietly orbiting, quietly waiting, for the day our instruments finally become precise enough to notice it. For now, we listen for the wobble. We watch for the dimming. And we wait. When astronomers began narrowing their search for another Earth, they had to make a choice. Out of the hundreds of billions of stars scattered across our galaxy, which ones offered the best chance of finding a small, rocky, potentially habitable world? Increasingly, the answer pointed toward a type of star that many people have never even heard of. Red dwarfs. Red dwarf stars are small, cool, and dim compared to our Sun. They do not burn with the same intensity, and they do not shine nearly as brightly across the vastness of space. But what they lack in brilliance, they more than make up for in sheer number. Red dwarfs are, by a wide margin, the most common type of star in our galaxy. Some estimates suggest they make up the vast majority of all stars in the Milky Way, far outnumbering stars like our own sun. And when a particular type of star is that common, it becomes an obvious place to search. Not because red dwarfs are guaranteed to host habitable planets, but simply because there are so many of them. Statistically, if even a modest fraction of red dwarf systems contain rocky, temperate worlds, the sheer abundance of these stars means the total number of potentially habitable planets could be enormous. This idea gained serious scientific weight in 2013, when researchers published a study examining just how common Earth-sized, potentially habitable planets might be around red dwarf stars. Their conclusion was striking. The study suggested that roughly 6% of red dwarf stars could host planets sitting within the habitable zone, small, rocky worlds, similar in size to our own, orbiting at just the right distance for liquid water to potentially exist. 6% might sound like a small number at first. But when you consider just how many red dwarf stars fill our galaxy, that 6% translates into an extraordinary quantity of potentially habitable worlds. Billions, by some estimates. Scattered quietly throughout the Milky Way, orbiting stars far dimmer and cooler than the one that warms our own planet. Perhaps even more remarkable was another conclusion drawn from that same study. Based on the statistical likelihood of these planets existing, researchers proposed that the very nearest Earth-like world could be astonishingly close, in cosmic terms. Possibly just 13 light-years away. 13 light-years. In the context of a galaxy that stretches over 100,000 light-years across, that distance is almost nothing. It is, relatively speaking, our galactic backyard. Close enough that, in theory, future telescopes with sufficient precision might eventually be able to study such a world in meaningful detail. Close enough that the idea of another Earth stopped feeling like a distant hypothetical and started feeling like a real, tangible possibility, hiding somewhere just beyond our current reach. Of course, red dwarf stars were not the only path forward in this search. Scientists were equally interested in stars more similar to our own sun, and it was around one such star that a genuinely historic discovery was made. In 2011, NASA announced something that had never been confirmed before. The first Earth-sized planets ever found orbiting a star similar to our Sun. This was a profound moment in the broader search for another Earth. Until that point, most confirmed exoplanets had been far larger than our own world, massive gas giants, or super-Earths considerably bigger than the planet we call home. But this announcement was different. For the first time, scientists had confirmed planets close to Earth's actual size, orbiting a star with characteristics similar to our own Sun. It was a signal, in many ways, that the search was maturing. That our tools were becoming precise enough to detect not just the largest, most obvious worlds, but smaller planets, more subtle in their signals, more similar in scale to our own quiet blue home. Much of this progress can be credited to the Kepler Space Telescope, which played an extraordinary role throughout this entire search. Kepler was not simply a tool for finding planets. It was a tool for reshaping how scientists understood the possibility of other worlds existing throughout the galaxy. Through its continuous monitoring of countless stars, Kepler helped demonstrate something profoundly important. that Earth-sized planets do exist within the habitable zones of other stars. Not just in theory, not just in mathematical probability, but in observed, confirmed reality. This achievement reached one of its most significant milestones with the discovery of a planet known as Kepler 186f. Kepler 186f holds a special place in the story of exoplanet science. It was the first confirmed Earth-sized planet ever found within the habitable zone of another star. Not simply a planet close to Earth's size. Not simply a planet somewhere in the general vicinity of a habitable region. But a planet meeting both criteria at once, roughly Earth's size, and positioned within that gentle zone where temperatures could theoretically allow liquid water to exist on its surface. Take a moment to consider what that discovery represented. For the very first time, scientists could point to a specific, confirmed world beyond our solar system and say, with real confidence, this planet is approximately the size of our own, and it orbits its star at a distance where conditions might, just might, be gentle enough to support liquid water. It did not prove that Kepler 186f was truly Earth-like in every sense. Its star was different from our Sun, dimmer and cooler, casting a different quality of light across that distant world. But in terms of size and position, it represented something the world had never confirmed before. Kepler 186f became, in many ways, a symbol. A quiet reminder that Earth-sized planets, in life-friendly orbits, were not simply theoretical possibilities. They were out there. Real. Waiting to be found. And Kepler's contributions did not stop there. In 2017, NASA released a significant update from the ongoing analysis of Kepler's data. The mission had identified 219 new planet candidates. 219 potential new worlds, waiting for further confirmation, hidden within the vast amount of data Kepler had collected over its years of continuous observation. Among those candidates, 10 stood out in a particularly meaningful way. These 10 planets were rocky, roughly Earth-sized, and situated in positions that made them potentially habitable. 10 worlds, out of that larger group of candidates, carrying the specific characteristics scientists hope to find when searching for another Earth. Rocky composition. A size similar to our own. And an orbit gentle enough to theoretically support the conditions life might need. It is worth pausing here to appreciate the scale of patience involved in reaching numbers like these. Every one of those 219 candidates began as nothing more than a faint, repeating dip in a star's brightness. A whisper of light, recorded again and again, analyzed carefully over time, until scientists could say with reasonable confidence that something real, something planetary, was there. And Kepler's discoveries continued to accumulate well beyond that particular announcement. In one notable release of findings, described within NASA's own overview of the mission's most remarkable achievements, Kepler was credited with the discovery of 95 new exoplanets in a single announcement. 95 new worlds, confirmed at once, each with its own size, its own orbit, its own quiet story hidden within the light of a distant star. Among that particular group of discoveries, one planet stood out for a very specific reason. It orbited the brightest star ever discovered by Kepler to host a transiting planet. brighter than any other star Kepler had used to detect a world crossing in front of it. There is something almost poetic about that detail. Out of the thousands upon thousands of stars Kepler observed throughout its mission, dim ones, distant ones, faint flickers scattered across the depths of space, this particular star shone more brightly than all the rest that had ever revealed a transiting companion. And hidden within that brilliance, quietly crossing that blazing light again and again, was a planet. Patiently orbiting. Waiting, in its own way, to be noticed. When you step back and consider everything uncovered through Kepler's work, the confirmation of Earth-sized worlds, the discovery of planets nestled gently within habitable zones, the identification of hundreds of new candidates, and the steady accumulation of newly confirmed exoplanets, one announcement after another, a clearer picture begins to form. The universe, it seems, is not sparse. It is not empty, scattered only with occasional planets here and there. It is abundant, filled, in ways we are only beginning to understand, with worlds of every imaginable size, temperature, and composition. Rocky planets, gaseous giants, planets orbiting close, and planets orbiting far. Planets around stars like our Sun, and planets around dim, quiet red dwarfs that outnumber all other stars combined. And somewhere among all of that abundance, among the trillion or so planets believed to exist within our galaxy alone, there may be a small number that closely resemble our own. Worlds with rocky ground beneath alien skies. Worlds sitting gently within their own habitable zones. Worlds we have only just begun to notice, thanks to the patient, careful work of missions like Kepler. We do not yet know their names, if names could even apply to places so far from us. We do not know what their surfaces look like, or whether liquid water truly exists somewhere upon them. But we know, now, in a way we did not fully know before, that such worlds are possible. That they are, in some form, out there. For now, let that thought settle gently over you, as the search continues quietly in the background, instruments listening for faint wobbles, watching for delicate dips in starlight, patiently gathering evidence, one small clue at a time. Somewhere among the countless stars scattered across the dark, a small rocky world may be turning slowly, gently, in an orbit not so different from our own, waiting, patiently, for the moment we finally learn its name. The story of Kepler was, in many ways, a beginning rather than an end. It proved that Earth-sized planets exist in habitable zones scattered throughout the galaxy. But proving something is possible is different from being able to study it closely. And so, the search for another Earth needed a new chapter. A new set of eyes turned toward the sky. That next chapter arrived with a mission called TESS. TESS stands for the Transiting Exoplanet Survey Satellite, though its full name matters less than what it was built to do. Where Kepler had spent years staring deeply at a single, fixed region of sky, patiently watching distant and often faint stars for the telltale signs of orbiting planets, TESS was designed with a different philosophy in mind. Rather than focusing narrowly on one small patch of the heavens, TESS was built to scan nearly the entire sky, searching specifically for planets orbiting stars that were bright and relatively close to us. This distinction may seem subtle at first, but it carries enormous significance. Bright Nearby stars are far easier to study in detail than the distant, dim stars Kepler often observed. When a star is close and luminous, astronomers can gather far more information about any planets found orbiting it. They can study the planet's atmosphere. They can estimate its composition with greater confidence. They can follow up with other telescopes, gathering deeper insights that would be nearly impossible for a planet orbiting a faint, far-off star, lost in the depths of the galaxy. In other words, TESS was not simply designed to find planets. It was designed to find planets we could actually get to know. When TESS began its mission, expectations were extraordinary. NASA anticipated that the spacecraft would monitor more than 200,000 stars, some of the nearest and brightest stars visible from Earth. 200,000 individual points of light, each one watched carefully for the faint, repeating dimming that signals a planet passing across its surface. Given that scope, scientists expected TESS to accomplish something remarkable. They projected that the mission would eventually help identify thousands of new exoplanets, an enormous contribution to our growing catalog of worlds beyond our solar system. Thousands of new planets, each with its own size, its own orbit, its own quiet secrets waiting to be uncovered through careful observation. And unlike many of Kepler's finds, which often required extensive additional studies simply to confirm basic details, the planets found by TESS were expected to be especially well suited for deeper investigation. Because their host stars were bright and nearby, these planets offered scientists a genuine opportunity to look closer, to study their atmospheres, to search for chemical signatures that might hint at their composition, or even, in time, at the possibility of habitability. This is part of what made TESS so valuable. It was not simply a numbers game, or race to catalog as many planets as possible. It was a mission built with the future in mind, designed specifically to identify targets that later, more powerful telescopes could study in far greater depth. TESS, in many ways, was laying the groundwork, preparing a list of promising worlds, so that the instruments of tomorrow would already know exactly where to look. And in 2020, that patient, methodical approach paid off in a deeply meaningful way. That year, TESS achieved something significant. It identified its first Earth-sized planet situated within the habitable zone of its star. A small, rocky world, similar in size to our own, orbiting at a distance where conditions might allow liquid water to exist. This discovery mattered for more than just its scientific details. It represented continuity. It showed that the search which began with Kepler, the search for small, temperate, Earth-like worlds, was continuing successfully into a new era, powered by a new generation of technology. Kepler had shown us that such planets exist. TESS was now confirming that they could be found again, and, crucially, found in a way that made them accessible for deeper study. When you consider both missions together, a broader truth begins to emerge. Earth-sized planets, nestled gently within the habitable zones of their stars, are not some rare fluke, discovered once and never seen again. They have now been found through multiple independent missions, using different instruments, different techniques, and different regions of the sky. Kepler found them. TESS has found them too. And each discovery adds another thread to a larger, more convincing pattern, a pattern suggesting that worlds like our own may not be nearly as rare as humanity once believed. But planets are only part of the story. To truly understand a distant world, scientists need more than just its size, and more than just its position within a habitable zone. They need to understand what that world is actually made of. What kind of atmosphere it might have, if any. What kind of light passes through that atmosphere, and what that light might reveal. This is where another remarkable instrument enters the story. NASA's Spitzer Space Telescope. Spitzer was different from Kepler and TESS in a fundamental way. Rather than observing the universe in visible light, the kind of light our eyes can naturally perceive, Spitzer was designed to observe the cosmos in infrared light. A different part of the electromagnetic spectrum entirely. Invisible to human eyes, but rich with information that visible light alone simply cannot provide. Infrared light allows scientists to detect heat. It allows them to peer through clouds of cosmic dust that would otherwise block our view entirely. And when it comes to studying exoplanets, infrared observations can reveal subtle details about a planet's temperature, and even hints about the composition of its atmosphere, in ways that traditional visible light observations often cannot. Spitzer launched in 2003, beginning a mission that would stretch on for many years, quietly reshaping our understanding of the universe in ways both large and small. And while Spitzer was not built specifically as an exoplanet hunting mission in the way Kepler or TESS were, it made substantial contributions to that field nonetheless. Following its launch, Spitzer helped scientists learn a great deal more about the exoplanets already being discovered by other missions. It contributed to our understanding of their atmospheres, their temperatures, the subtle variations that separate one distant world from another. In many cases, Spitzer served almost like a companion to other telescopes, adding depth and detail to discoveries that had first been identified through the transit method or the radial velocity method, filling in details that those techniques alone could not fully capture. Together, these missions, Kepler, TESS, and Spitzer, reveal something important about how scientific discovery truly works. No single telescope, no single mission, uncovers the full picture on its own. Each instrument contributes its own perspective, its own strengths, its own particular way of observing the universe. Kepler proved that Earth-sized, habitable zone planets exist. TESS expanded that search across brighter, closer stars, offering planets that could be studied in far greater depth. And Spitzer, observing in a different wavelength of light entirely, added new layers of understanding to the worlds these other missions had found. It is, in many ways, a quiet collaboration stretched across decades. Different instruments, launched years apart, each building upon the discoveries of those that came before. A kind of patient, generational effort, not driven by any single moment of triumph, but by the slow, steady accumulation of understanding. And it continues even now, in the quiet hours, while much of the world sleeps. Somewhere above us, spacecraft drift silently through the dark, their instruments fixed on distant points of light. Watching, measuring, recording faint patterns that may take years to fully understand. Consider, for a moment, just how much patience this entire endeavor requires. missions conceived years before their launch. Telescopes that operate for over a decade, slowly gathering data one small observation at a time. Scientists analyzing that data long after a mission has ended, still finding new discoveries buried within old records. It is not a search built for immediate answers. It is a search built for the long and steady unfolding of understanding, a process measured not in days, but in years, and sometimes in decades. And yet, piece by piece, that patient effort continues to bring us closer. Closer to understanding just how common small, rocky, temperate worlds might be. Closer to identifying which of those worlds might be worth a much closer look. And closer, perhaps, to the day when a telescope powerful enough finally reveals not just the size and orbit of a distant planet, but real, tangible details about its atmosphere, details that might tell us, at last, whether a world truly resembles our own. For now, that day has not yet arrived. But the groundwork has been laid, mission by mission, telescope by telescope, across more than 2 decades of careful, dedicated work. So let your thoughts drift gently along with those distant spacecraft, quietly orbiting far above, watching countless stars in patient silence. Somewhere among the light they gather, hidden within faint dips and subtle infrared glows, another world may be waiting. Quiet. Rocky. Familiar, in ways we have not yet fully discovered. And little by little, we are learning how to find it. There is one discovery, among all the findings we've explored so far, that stands apart. Not because of a single planet, but because of an entire system, a family of worlds, unlike anything scientists had confirmed before. It began with NASA's Spitzer Space Telescope, the same infrared observatory that had spent years quietly adding depth to our understanding of distant worlds. And in one particular observation, Spitzer revealed something remarkable. A single star, orbited not by one Earth-sized planet, not by 2 or 3, but by 7. 7 Earth-sized planets, circling the same star. The first system of its kind ever confirmed. Take a moment to imagine that. A single star, hosting not a lone Earth-like world, but an entire collection of them. 7 planets, each roughly similar in size to our own, orbiting together in a tightly arranged, delicately balanced system. It was unlike anything astronomers had encountered before, a discovery that immediately reshaped how scientists thought about the potential abundance of Earth-sized worlds throughout the galaxy. This system quickly became one of the most closely studied targets in the entire search for possible life beyond our solar system. And it earned a name that has since become widely recognized among those following this field. TRAPPIST-1. The TRAPPIST-1 system captured scientific attention for a very specific reason. Several of its 7 planets are roughly Earth-sized, not gas giants, not distant icy worlds far larger than our own, but planets whose scale closely resembles the ground beneath our feet. NASA highlighted this system as one of the most significant exoplanet discoveries of its time, precisely because of this remarkable arrangement. 7 planets. Roughly Earth-sized. Orbiting closely around a single, dim star. The star itself, much like many of the systems we discussed earlier, is a red dwarf, small, cool, and common throughout our galaxy. And nestled around that quiet star, its 7 planets orbit in relatively close formation, some of them positioned in or near the habitable zone, where conditions might allow liquid water to exist. It is worth pausing here to appreciate the scale of what this discovery represents. Not just one potentially interesting world, but several, all within a single, tightly packed system. If you were to stand on the surface of one of these planets and look up into its sky, you might see not just a distant star, but the visible disks of neighboring planets, other worlds, close enough to appear as more than mere points of light. A sky filled with sibling planets, drifting nearby in their own quiet orbits. TRAPPIST-1 remains, to this day, one of the most extensively studied systems in the search for potentially habitable worlds. And its discovery reinforced something increasingly clear throughout this entire search. Earth-sized planets are not isolated anomalies, appearing once in a great while, scattered thinly across the galaxy. They can exist in clusters, in families, multiple worlds, of similar size, orbiting the very same star. But TRAPPIST-1, remarkable as it is, was not the only major announcement to capture the world's attention. In 2016, scientists revealed another discovery, one made all the more striking by its sheer proximity to us. A planet called Proxima Centauri b. This planet orbits Proxima Centauri, the very closest star to our own Sun. Not simply close in a general cosmic sense, but literally the nearest star to our solar system, a quiet red dwarf drifting through space just a short distance away, in astronomical terms. Proxima Centauri b was announced as an Earth-mass planet, positioned within the habitable zone of its star. A planet with a mass similar to our own world, orbiting at a distance where temperatures might allow liquid water to exist on its surface. What made this discovery especially significant was not simply the planet's characteristics, but its location. Because Proxima Centauri sits so close to our own solar system, relatively speaking, this planet became, almost instantly, one of the most compelling and accessible targets in the entire search for another Earth. A potentially habitable world, orbiting the very nearest star beyond our own Sun. Of course, proximity alone does not confirm habitability. A planet's mass, and its position within a habitable zone, tell us only part of the story. To understand whether a world is truly capable of supporting life, scientists need much more detailed information. They need to understand its atmosphere, if it possesses one at all. They need to search for specific chemical signatures that might hint at conditions suitable for life, or perhaps, in the most extraordinary of cases, hint at life itself. This is where an entirely new kind of investigation enters the story. One that moves beyond simply detecting a planet's existence, and begins to examine what that planet is actually like. Remarkably, scientists have found a way to study a planet's atmosphere, even from such immense distances. It happens during the very same transit event used to detect a planet's presence in the first place. As a planet passes in front of its star, a small amount of that starlight does not simply get blocked. Instead, it passes directly through the planet's atmosphere, if one exists, on its way toward Earth. As that starlight filters through an alien atmosphere, certain wavelengths of light become absorbed by specific molecules present within that atmosphere. Different molecules absorb different wavelengths of light, creating a kind of chemical fingerprint hidden within the starlight that eventually reaches our telescopes. By carefully analyzing that filtered light, scientists can identify traces of specific molecules present in a distant planet's atmosphere, substances like water vapor or oxygen, each leaving behind its own subtle, telltale signature. It is an extraordinary technique when you consider what it truly represents. Light, traveling across trillions of miles of empty space, carrying within it faint chemical clues about a world we will likely never visit in person. A message, of sorts, written not in words, but in the subtle absorption patterns hidden within starlight itself. Using this technique, scientists now study distant atmospheres for a wide range of clues. They search for water. They search for carbon-based molecules. They search for any chemical signature that might offer insight into a planet's composition, its climate, and its potential capacity to support life as we understand it. At the heart of this search lies a particular concept that has become central to modern astrobiology: biosignatures. A biosignature is a chemical clue, a specific molecule or combination of molecules, whose presence might suggest that life could be present on a distant world. Certain gases, when found together in particular proportions within a planet's atmosphere, are difficult to explain through non-biological processes alone. Their presence does not prove that life exists. But it raises a compelling possibility, worth investigating further. Researchers continue this search patiently, examining the atmospheres of distant worlds for exactly these kinds of chemical clues. It is delicate, painstaking work, requiring an extraordinary level of precision. But it represents, perhaps more than any other technique discussed so far, our closest approach yet to answering that fundamental question: are we alone? And in recent years, this search has been transformed by the arrival of an entirely new tool. One capable of examining these distant atmospheres with a level of detail previous instruments could never achieve. The James Webb Space Telescope. Webb represents a profound leap forward in our ability to study exoplanet atmospheres. Where earlier telescopes could sometimes detect only hints, faint traces buried within noisy data, Webb possesses the sensitivity and precision to examine these atmospheres in far greater detail. It can capture subtler signals, identify a wider range of molecules, offer scientists a clearer, more confident picture of what these distant worlds might actually be like. Already, NASA's James Webb Space Telescope has measured the atmospheres of several exoplanets in remarkable detail, studying their chemical composition with a precision that was simply unavailable to earlier generations of instruments. Each observation adds new layers of understanding, slowly refining our picture of these distant worlds, one careful measurement at a time. When you consider the full arc of this story, from Spitzer's discovery of that first remarkable 7-planet system, to the close and tantalizing possibility of Proxima Centauri b, to the delicate art of reading a planet's atmosphere through the light that passes through it, and finally, to the extraordinary capabilities of the James Webb Space Telescope, a clear pattern begins to emerge. We are no longer simply asking whether Earth-like planets exist. We already know that they do, or at least, that worlds remarkably similar in size and position exist throughout our galaxy. the question has shifted. It has become more precise, more focused. We now ask what these worlds are actually like, what their atmospheres contain, whether the delicate chemical signatures of life might be hidden somewhere within that faint, filtered starlight. It is a search that grows more refined with each passing year. Each new telescope, each new technique, each new discovery bringing us incrementally closer to an answer that has captivated humanity for as long as we have looked up at the night sky and wondered. Somewhere out there, perhaps orbiting a quiet red dwarf, perhaps nestled among 7 sibling worlds, perhaps circling the very nearest star beyond our own sun, a planet may be waiting. Its atmosphere holding secrets we are only just beginning to learn how to read. And with each passing observation, each careful measurement gathered by instruments like the James Webb Space Telescope, we come a little closer to understanding what those secrets might be. For now, let the thought rest gently in your mind. Starlight, traveling for years, sometimes decades, across the emptiness of space, carrying within it the faintest whisper of another world's atmosphere, waiting patiently for us to learn how to listen. One of the clearest signs that we have entered a new era in this search came not from the discovery of a new planet, but from a detailed look at one already known. WASP 39b is a planet that had been studied for some time before the arrival of the James Webb Space Telescope. But when Webb turned its extraordinary instruments toward this distant world, it revealed something that older telescopes simply could not detect with the same clarity. Carbon dioxide, present within the planet's atmosphere. This might sound like a small, technical detail, but its significance runs much deeper than it first appears. Detecting carbon dioxide in a distant planet's atmosphere demonstrates, with remarkable clarity, just how precise our instruments have become. It is one thing to detect the presence of a planet through a faint dimming of starlight. It is an entirely different achievement to identify the specific molecules drifting within that planet's atmosphere, trillions of miles away, based on nothing more than filtered starlight passing gently through those distant gases on its long journey toward Earth. This discovery, made possible by Webb, represents a preview of what lies ahead. Because if carbon dioxide can be detected with this level of confidence, it opens the door to identifying other molecules as well. Water vapor. Methane. Perhaps, eventually, the kinds of chemical signatures that hint at biological processes, the elusive biosignatures scientists have been searching for. New telescopes, and the future observatories still being planned and developed, continue building upon this momentum. Each new instrument is designed with a similar goal in mind: to look more closely at distant atmospheres, to search for signs of rocky surfaces, similar in composition to our own world, and, ultimately, to search for any possible indication that life might exist somewhere beyond our solar system. And yet, even with all of this remarkable progress, scientists remain candid about the limitations we still face. Despite everything we have learned, astronomers acknowledge that we still need better instruments and more refined analysis tools before we can confidently detect a true Earth analog, a planet that does not just resemble Earth in size or general position, but one that closely matches our world across a much broader range of characteristics. Atmosphere, composition, climate, the delicate balance of conditions that allows a planet to sustain the kind of stable, temperate environment life as we understand it seems to require. This honesty matters. It would be easy, given how far this field has come, to assume that finding a true Earth twin is simply a matter of time, a foregone conclusion waiting patiently just around the corner. But the reality is more nuanced. Every discovery so far, from Kepler 186f to TRAPPIST 1 to Proxima Centauri b, has brought us closer. Each has offered pieces of the picture we're trying to assemble. But the full picture, a planet confirmed to closely mirror Earth in nearly every meaningful way, remains, for now, just beyond our grasp. Reaching that goal will require not only better telescopes, but also smarter, more efficient ways of analyzing the enormous amounts of data those telescopes continue to gather. This is where an unexpected tool has begun to play an increasingly important role: machine learning. In recent years, astronomers have started using machine learning techniques to help validate new exoplanets, and the results have been remarkably effective. Traditionally, confirming a new exoplanet required extensive manual analysis, researchers carefully examining light curves, checking for consistency, ruling out alternative explanations one by one. This process, while thorough, was often slow, painstaking. A task that could take months, sometimes longer, for a single candidate. Machine learning has begun to change that. By training computer models on vast amounts of existing exoplanet data, scientists have developed systems capable of recognizing patterns far more quickly than traditional manual methods ever could. These systems can sift through enormous datasets, flagging likely candidates with impressive accuracy, allowing human researchers to focus their attention more efficiently on the most promising signals. It represents a quiet but meaningful shift in how this search unfolds. Not replacing the careful, patient work of astronomers, but accelerating it. Helping humanity process the sheer scale of data now being collected, data that, quite simply, would be impossible to examine manually within any reasonable amount of time. And that scale of data continues to grow, because our understanding of planetary systems remains far from complete. Scientists have not yet fully mapped out the true complexity of planetary systems throughout our galaxy. Every new discovery seems to reveal further nuance, unexpected planet sizes, unusual orbital arrangements, atmospheric compositions that defy easy categorization. This ongoing complexity is precisely why the search for Earth analogs continues with such determination. We are not simply looking for confirmation of something we already fully understand. We are still learning the basic shape of what exists out there, even as we search for something as specific and meaningful as another Earth. This search is about to enter a particularly important new phase, with the upcoming launch of NASA's Roman Space Telescope. Roman is expected to represent a major advance in the ongoing hunt for exoplanets. Its capabilities are designed to expand this search well beyond what missions like Kepler and TESS have achieved so far, surveying vast regions of the sky with a level of scope and sensitivity that promises to reshape our understanding of just how many planets exist throughout our galaxy. The scale of Roman's expected contribution is genuinely difficult to comprehend. NASA anticipates that this single mission could reveal around 100,000 new worlds. 100,000. A number that would represent an extraordinary leap forward compared to the total number of exoplanets confirmed throughout the entire history of this field so far. Take a moment to consider the significance of that projection. Every mission we've discussed throughout this journey, Kepler, TESS, Spitzer, even the remarkable work of the James Webb Space Telescope, have collectively contributed to a catalog that, while impressive, remains relatively modest compared to what Roman alone is expected to add. If these projections hold true, Roman could single-handedly transform the scale of our exoplanet catalog, opening up possibilities we are only beginning to imagine. And this leads to an important, often overlooked detail about the current state of the search. Despite everything discovered so far, most known exoplanets have been found within a relatively small region of our galaxy. Not scattered evenly across the full breadth of the Milky Way, but concentrated largely within specific areas that our current missions have been capable of observing in sufficient detail. This detail matters enormously, because it reframes everything we've discussed so far. Every planet mentioned throughout this entire journey. Kepler 186f, TRAPPIST 17 worlds, Proxima Centauri b, WASP 39b, represents only a small sample, drawn from a relatively narrow slice of our galaxy's true scale. The Milky Way stretches across more than 100,000 light-years. And yet, the vast majority of confirmed exoplanets have been found within a comparatively tiny portion of that immense span. This means the search, remarkable as it has been so far, has really only just begun. There remain enormous, largely unexplored regions of our own galaxy, filled with countless stars we have not yet studied closely enough to detect their planets at all. It is worth pausing here to reflect on how far this field has come, even while acknowledging just how much further it still has to go. At one point during this ongoing search, the number of confirmed exoplanets passed a meaningful milestone, crossing beyond 3,700 confirmed worlds. A number that, not long before, would have seemed almost unimaginable, considering that the very first confirmed exoplanet around a Sun-like star was only discovered in 1995. And the pace of discovery has only continued to accelerate since then. In March of 2022, NASA announced an even more significant milestone. The total number of confirmed exoplanets had officially passed 5,000. 5,000 confirmed worlds. Each one representing a small, hard-won victory in a search built on patience, precision, and years of careful observation. Each one beginning as nothing more than a faint dimming of starlight, or a barely detectable wobble in a distant star's motion, painstakingly analyzed, confirmed, and added to a growing catalog that continues to expand with each passing year. When you consider the full scope of this journey, from that first tentative discovery in 1995, to the confirmation of Earth-sized worlds through missions like Kepler and TESS, to the extraordinary atmospheric detail now being revealed by the James Webb Space Telescope, to the anticipation building around future missions like Roman, a clear and remarkable pattern begins to emerge. We are living through an extraordinary chapter in human history. A chapter in which the ancient question of whether other worlds exist has already been answered, decisively, again and again. They do exist. Thousands of them, confirmed. and likely trillions more, scattered throughout our galaxy alone, waiting patiently for the moment our instruments become precise enough to notice them. The deeper question now, the one occupying so much of modern astronomy's attention, is no longer simply whether other worlds exist. It is which among those countless worlds might closely resemble our own. Which ones might hold atmospheres capable of supporting liquid water? Which ones, if any, might carry the delicate chemical signatures that suggest life has found a way to exist somewhere beyond our quiet, blue planet? We do not have that answer yet. Not with certainty. But every mission, every discovery, every careful measurement brings us incrementally closer. Roman has not yet launched. Its full catalog of 100,000 potential worlds remains, for now, just beyond the horizon, waiting to be revealed. But when that mission does begin its work, it may very well mark the next great leap forward in this remarkable, ongoing search, one that has already reshaped how humanity understands its place within an unimaginably vast and abundant galaxy. For now, we rest in this quiet moment of anticipation. 5,000 confirmed worlds behind us. Countless more waiting patiently ahead. Somewhere among them, hidden within the light of a star we have not yet studied closely enough, there may be a planet remarkably similar to our own, a true Earth analog, waiting for the day we finally develop the tools precise enough to recognize it. Until that day arrives, the search continues, quietly, patiently, one faint signal at a time, carried gently across the vast and silent dark, toward instruments here on Earth that are only growing more capable of listening. Numbers, on their own, can feel abstract, distant, easy to hear and just as easy to forget. But when you follow them closely, one milestone after another, they begin to tell a story. A story of steady, unwavering progress, carried forward year after year, by scientists who never stopped watching the sky. We left off with a significant achievement. The confirmed count of known exoplanets passing 5,000, announced by NASA in March of 2022. At the time, that milestone felt monumental. And it was. But the search, as we've come to understand throughout this journey, does not pause. It does not rest on past achievements. It simply continues, quietly, methodically, adding new discoveries to an ever-growing catalog. And so, just over a year later, another milestone arrived. The count passed 5,500. This next chapter in the story unfolded in July of 2024, when NASA announced that the total number of confirmed exoplanets had officially crossed that new threshold. 5,500 confirmed worlds, each one representing its own careful process of detection, observation, and confirmation. What makes this particular milestone especially interesting is not simply the number itself, but how it was reached. This threshold was crossed not through the addition of a single planet, but through the announcement of 6 new exoplanets, added together in a single moment. 6 new discoveries, confirmed at once, pushing the total count to 5,502. There is something quietly satisfying about that detail. After years of individual discoveries, each one requiring its own confirmation, its own patient verification, this milestone arrived through a small cluster of worlds, revealed together, as if the universe had offered up 6 new secrets all at once. Behind this achievement lies NASA's Discovery Dashboard, a resource that tracks exoplanet discoveries as an ongoing, evolving record. Not a static list, fixed and unchanging, but a living document, constantly updated as new research is confirmed and added. It reflects, in many ways, the true nature of this entire field. A search that never truly concludes. One that continues to grow, quietly and steadily, with each passing month. Since that milestone in 2024, the count has continued climbing. Today, NASA's exoplanet catalog contains more than 6,000 confirmed exoplanets. 6,000 distinct worlds, each cataloged, each verified, each representing its own small contribution to humanity's growing understanding of the galaxy around us. It is worth pausing here to consider what that word, confirmed, truly means within this context. Because not every claimed discovery makes it onto this list. The NASA Exoplanet Archive maintains a particular standard. It only counts worlds that have been confirmed through peer-reviewed scientific work. This distinction matters a great deal. It means that every single planet included in that catalog of more than 6,000 worlds has been examined, scrutinized, and verified by the broader scientific community, not simply proposed, or suspected, or tentatively identified, but rigorously confirmed through a process designed to filter out uncertainty and error. This is part of what makes the steady growth of this catalog so meaningful. Each new edition represents real, verified evidence, not speculation, not preliminary data waiting for further study, but confirmed knowledge, carefully reviewed by researchers before being accepted into the official record. Returning to that milestone moment in 2024, when the count reached 5,502, there is another detail worth appreciating. Those 6 new planets did not come from a single research team, working in isolation. They emerged from 5 separate studies, conducted by different teams of scientists, working independently, likely unaware that their individual findings would combine to cross such a significant threshold at the very same time. There is something quietly beautiful about that image. Researchers scattered across different institutions, perhaps in different countries, each pursuing their own careful analysis of distant starlight, unaware that their separate efforts were converging toward the very same historic moment. Science, in this sense, often unfolds not through singular, isolated breakthroughs, but through countless independent efforts, each contributing its own small piece to a much larger, shared achievement. Among those 6 newly confirmed worlds, one planet in particular stands out for its unusual characteristics. A planet known as HD 36384b. This planet is what astronomers call a super-Jupiter, a gas giant considerably larger and more massive than Jupiter itself, the largest planet within our own solar system. Already, that description alone paints a picture of considerable scale. But what makes HD 36384b especially notable is not simply its own size, but the nature of the star it orbits. HD 36384b orbits an enormous star known as an M-giant. This is a particular late stage in a star's life, when it has expanded dramatically, growing into an immense, swollen giant, far larger than it once was during its earlier years. M giants represent stars that have evolved considerably from their earlier, more compact form, stars that have grown outward, becoming vast, luminous giants as they progress through the later stages of their stellar life cycle. Try to imagine that scene for a moment. A super Jupiter, itself an enormous world by any standard, quietly orbiting a star so vast that it dwarfs our own sun many times over. Two extremes of scale, existing together within the same distant system, a massive planet, circling an even more massive, swollen star, far out among the countless other systems scattered throughout our galaxy. It is discoveries like this one that remind us just how varied, just how strange, and just how wonderfully unpredictable the universe truly is. Not every new addition to this growing catalog resembles a small, rocky, potentially habitable world like the ones we've explored earlier in this journey. Some, like HD 36384b, represent something entirely different, a glimpse into the more extreme, more dramatic possibilities that exist among the countless stars scattered throughout the Milky Way. And yet, each of these discoveries, whether a small rocky world nestled gently within a habitable zone, or a massive super-Jupiter orbiting an enormous, aging star, adds another piece to the same overarching story. A story of a galaxy far more diverse, far more abundant, and far more surprising than humanity ever imagined, before we developed the tools capable of looking closely enough to notice. When you step back and consider this entire arc, from that very first confirmed exoplanet in 1995, through the steady climb toward 5,000 confirmed worlds, and now onward past 6,000, a clear pattern begins to emerge. This search is not slowing down. If anything, it continues to accelerate, propelled by increasingly powerful telescopes, increasingly refined techniques, and increasingly sophisticated tools capable of sifting through enormous quantities of astronomical data. Every new milestone, every new cluster of confirmed planets, adds further weight to an idea that has grown more certain with each passing year. Our galaxy is not sparse. It is not quiet, in the way humanity once assumed, back when we knew of no planets beyond our own solar system at all. It is teeming, in ways both grand and subtle, with worlds of every conceivable size, composition, and character. Some of those worlds are small and rocky, quietly orbiting within gentle habitable zones, waiting for us to study their atmospheres in greater detail. Others are massive and dramatic, like HD 36384b, orbiting stars that have grown into enormous, swollen giants far different from the stable, steady sun that warms our own world. And somewhere among all of that diversity, hidden within a catalog that continues to grow past 6,000 confirmed worlds, there may still be a planet waiting to be discovered, one that finally matches our own world closely enough to answer, with real confidence, that ancient and quiet question humanity has asked for as long as we have looked upward into the night sky. For now, the catalog continues to grow. 6,000 worlds confirmed, and counting. Each one a small, hard-won piece of a much larger puzzle, a puzzle that stretches across the entire galaxy, patiently waiting for us to keep looking, keep listening, and keep searching, for that one particular world that might, at last, feel a little more like home. Let's return, for a moment, to that star we mentioned earlier. The one hosting HD 36384b, that unusual super-Jupiter discovered among the 6 new worlds that helped push the exoplanet catalog past 5,500 confirmed planets. We know now that this planet orbits an M-giant, a star in the later, expanded stage of its stellar life. But the true scale of that star is worth sitting with a little longer, because the numbers involved are almost difficult to fully comprehend. This star is nearly 40 times the size of our own Sun. 40 times. Try to picture that for a moment. Our Sun, already so large that more than 1 million Earths could fit inside its volume, would itself appear small and modest beside a star this immense. A star that has swollen outward over the long course of its evolution, expanding into something vast, luminous, and almost unimaginable in scale. And somewhere within the gravitational reach of that enormous star, HD 36384b continues its quiet orbit, a massive planet in its own right, yet still dwarfed entirely by the sheer size of the star it circles. It is a reminder of just how varied stellar life can be. Stars are not fixed, unchanging points of light. They evolve. They grow. And in their later years, some expand into scales that reshape everything orbiting around them. But HD 36384b was only one of 6 remarkable discoveries announced together during that milestone moment. And the others offer their own distinct stories, each expanding our understanding of just how diverse planetary systems throughout the galaxy can be. Among these newly confirmed worlds was a planet known as TOI 198b. TOI 198b stood out for a particular reason. Scientists described it as a potentially rocky planet, positioned near the inner edge of its star's habitable zone. This detail carries meaningful significance. Being near the inner edge of a habitable zone means the planet sits close enough to its star that conditions may run warmer than what we might consider ideal, yet still within the range where liquid water could theoretically persist under the right circumstances. It is a delicate position. Not comfortably centered within that gentle, temperate band scientists often look for, but not entirely outside of it either. A planet balanced along the edge of possibility, potentially rocky in composition, and orbiting just close enough to raise genuine scientific interest. This is part of what makes the search for Earth-like worlds so intricate. Habitable zones are not simple, fixed lines drawn neatly around a star. They exist along a spectrum, with inner and outer boundaries that shift depending on a star's size, temperature, and brightness. A planet like TOI 198b, sitting near that inner edge, represents one of the many nuanced possibilities scientists must carefully evaluate, rather than a simple, clear-cut case of habitability confirmed or denied. The same announcement also introduced 2 additional planets, orbiting within a single shared system. TOI 2095b and TOI 2095c. These 2 worlds, discovered together within the same planetary system, share a notable characteristic. Both are large, hot super-Earths. Planets larger than our own world, orbiting close enough to their star that surface temperatures are likely far too extreme to resemble anything close to Earth's gentle, temperate climate. There is something interesting about finding 2 such planets within the very same system. It suggests a particular kind of architecture, a star surrounded not by a single notable world, but by multiple planets of a similar general category, both large, both hot, both quite different from the small, temperate worlds most closely associated with habitability. Systems like this remind us that planetary formation does not follow a single, universal pattern. Some systems, like TRAPPIST-1, produce multiple small, Earth-sized worlds clustered closely together. Others, like this one, produce pairs of larger, hotter super-Earths, shaped by different conditions during their formation, and settled into orbits quite unlike anything found within our own solar system. Among the 6 newly announced worlds, one planet in particular stood out for an entirely different reason, not its potential habitability, and not its size, but its truly unusual orbit. TOI 4860b is a gas giant, roughly comparable in size to Jupiter. But unlike Jupiter, which takes nearly 12 years to complete a single orbit around our Sun, TOI 4860b completes one full orbit around its star in just 1.52 days. Let that sink in for a moment. A planet, similar in size to the largest planet in our own solar system, racing around its star in under 37 hours. An entire year on that planet passes by faster than a single weekend here on Earth. What makes this discovery especially significant is not simply the short orbital period on its own, but the type of star this massive planet orbits. TOI 4860b circles an M-dwarf star, one of those small, cool, common red dwarf stars we discussed earlier in this journey. And finding a planet this large, orbiting this closely, around a star this small, is considered genuinely rare. M-dwarf stars are far smaller and less massive than stars like our Sun. Under most circumstances, it would be unusual for such a small star to host a planet as large as Jupiter in the first place, let alone one locked into an orbit so remarkably tight. And yet, here it is. A massive gas giant, circling a small, dim star at an astonishingly close distance, completing its entire year in a little over a single day and a half. Discoveries like TOI 4860b challenge scientists to reconsider certain assumptions about how planetary systems typically form and evolve. It stands as a reminder that the universe rarely follows expectations perfectly. For every pattern astronomers begin to identify, exceptions like this one eventually appear, unusual, unexpected, and quietly fascinating in their rarity. And finally, among these 6 remarkable discoveries, one held a particularly unique distinction. Rather than representing a fully formed, mature planet, this final world was still in the process of being born. The announcement included a giant protoplanet, a planet still forming, within a young and developing planetary system. This detail offers a rare and valuable glimpse into an entirely different stage of a planet's existence. Every planet we have discussed throughout this journey, from Kepler 186f to TRAPPIST-1's 7 worlds, to Proxima Centauri b, exists today as a fully formed world, shaped by billions of years of gradual development. But a protoplanet represents something different. A world still taking shape, still gathering material from the surrounding disk of gas and dust that swirls around its young star, still in the earliest stages of becoming what it will eventually be. Observing a protoplanet offers scientists a unique opportunity, a chance to study planetary formation not through inference or theoretical modeling alone, but through direct observation of the process actually unfolding, captured at a specific, active moment in a young system's development. It is, in some ways, like catching a glimpse of creation itself, still in progress. A reminder that the planets we discuss throughout this journey, worlds like Earth included, were not always fully formed, stable, and complete. Every planet, at some point in its distant past, existed only as scattered material, gradually accumulating, gradually taking shape, over the course of countless years within a young and still evolving system. When you consider all 6 of these discoveries together, HD 36384b, orbiting its immense, swollen host star, TOI 198b, balanced delicately near the inner edge of habitability, the paired super-Earths of the TOI 2095 system, the astonishingly fast orbit of TOI 4860b, and finally, a giant protoplanet, still forming within its youthful system, a striking picture begins to take shape. These 6 worlds, announced together in a single moment, represent an extraordinary range of possibility. Massive planets orbiting massive, aging stars. Potentially rocky worlds balanced along the delicate edge of habitability. Paired super-Earths, sharing a single system. Gas giants completing entire orbits within a matter of hours. And planets still being born, captured mid-formation, offering rare insight into processes that shaped every world we know, including our own. It is a vivid reminder of just how much diversity exists within our galaxy. Not every discovery brings us closer to finding another Earth directly, but each one adds depth, context, and understanding to the broader picture, helping scientists refine their knowledge of how planetary systems form, evolve, and vary, one discovery at a time. And within that ever-expanding tapestry of worlds, the search for a true Earth analog continues quietly in the background, patient, persistent, and steadily growing more precise with each new system studied, each new planet confirmed, and each new milestone reached along the way. For now, let your thoughts rest gently on that image, a swollen giant star, nearly 40 times the size of our Sun, quietly holding a massive planet in its orbit. And nearby, scattered across the galaxy, smaller worlds continuing their own quiet formation, slowly, patiently, becoming whatever they are destined to be.